Hello, my name is John Cody. I'm an engineer from Vancouver, Canada. In the past, I've been following a mathematics channel by Professor Norman Wildberger. His channel is called Insights into Mathematics, and I've been following the universal hyperbolic geometry material he presents there on YouTube. Recently, he created a new channel called Wild Egg Maths, and he's invited amateurs and the public to explore research level maths. And the material I'm going to present here is my first findings from in the field of projective geometry. So the formula I've come across or discovered is what I'm calling the projective double cross formula. And here it is right here. This is the projective double cross formula, and the way we arrive at it is by combining two projective triangles to form a projective quadrilateral. The quadrilateral has points A1, A2, A3, A4, and it has side quadrants Q1, Q2, Q3, and Q4. And the spreads S2 at point 2 and S4 at point 4. And this is the projective double cross formula that pertains to this quadrilateral. Now, this projective double cross formula can be rewritten and reformulated in more symmetric form. This is the symmetric form of the projective double cross formula. And this is it right here. Okay, so how do I create these formulas? Well, I followed the material in this course on having to do with the projective quadruple quad formula. So I'll present that now, the background material. So in his video, Math Foundations number 148, he presented the projective quadruple quad formula, and the ingredients that went into it are the Quadratic Compatibility Theorem, and that states if you have two quadratic equations, these two equations right here, they are compatible, meaning they have a common solution x, when this equation, Archimedes function, is satisfied. So this is Archimedes function right here. If this equation is satisfied, then these two quadratic equations are compatible, meaning they have a common solution x. So let's see how he applied it in his Math Foundations 148. He started with two triple quad formulas right here, which are in this form. These are two quadratic equations in P, and when you take the values from these two equations and put them into this formula, then you arrive at the Quadratic Compatibility Theorem. So what he's doing here is there's two triple quad formulas. They're written in an alternate form. They're in the quadratic completed the square form. So the first one pertains to, if we have four projective points, A1, A2, A3, A4, then there's a quad triple, A1, A2, and A3. The quadrants between Q1 and between A1 and A2 is Q1, between A2 and A3 is Q2, and between A1 and A3 is P. So the first equation is a triple quad formula consisting of Q1, Q2, and P. The second equation is a triple quad formula consisting of the points A1, A3, and A4. So the quadrants between A1 and A3 is P. The quadrants between A3 and A4 is Q3. And the quadrants between A1 and A4 is Q4. So that these two, and that forms another triple quad formula. So these two triple quad formulas have a common solution P when you put these quantities from here into this equation, and you get this value right here, which is the quadruple quad formula. And here it is in a more symmetric form of the projective quadruple quad formula. Okay, so next I will show you. Basically I followed the same procedure he did for creating the projective quadruple quad formula for my solution for finding the projective double cross formula. Okay, so the first thing we need to do is we start with the projective cross law. So here we have a projective triangle with points A1, A2, and A3. And side quadrants is Q1, Q2, and Q3. And here is the spread at point A3. So right here, this is the cross law, the projective cross law. Okay, and what we need to do is put it into an alternate form, and here's our two alternate forms of the projective cross law. And this form here is it's a quadratic equation in Q3, and this is in the form where you've completed the square. So here we have Q3 minus something all squared equals something not involving Q3. Okay, so that's the first step in coming up with the projective double cross law, is we need to use the alternate form of the projective cross law. So next, so what we've done here we have two projective triangles with a common edge, Q5, and these two projective triangles, when you combine them together, they form a quadrilateral. So the quadrilateral has points A1, A2, A3, and A4. Side quadrants is Q1, Q2, Q3, Q4, and spread at point A2 is S2, and the spread at point A4 is S4. And they have a common edge between A1 and A3, which has a quadrant of Q5. So we're going to apply the quadratic compatibility theorem. First, the first equation here involving Q1, Q2, and Q5. This is the alternate form of the cross law for this first triangle up here. This is the alternate form of the cross law for the second projective triangle. So in this alternate form, we have a common solution Q5. These two equations by the quadratic compatibility theorem are compatible, meaning they have a common solution Q5. Then we just need to plug these quantities into the Archimedes formula, which is the triple quad formula in the affine case. And when we do that, so by the quadratic compatibility theorem, when we plug these two alternate forms of the cross law into the quadratic compatibility theorem, then we arrive at the projective double cross law. And so here's the projective double cross law. And down here is the symmetric form of the projective double cross law. And I will point out that when you set the spreads equal to the spread S2 and S4, when they are set to 0, then the projective double cross law simplifies to the projective quadruple quad formula. And same thing for the symmetric form of the projective cross law. If you set the spreads S2 and S4 to 0, then you'll arrive at the projective quadruple quad formula, the symmetric form of that. Okay. Now, we could also start with this form of the quadrilateral, where we're using this chord, the common edge Q6 between A2 and A4. So then we have this projective triangle here and another projective triangle here. And so this is, this projective triangle corresponds, this is the cross law, the alternate form of the cross law for this projective triangle. And this is the alternate form of the cross law for the second projective triangle. And again, by the quadratic compatibility theorem, we can plug these quantities directly into Archimedes' function, and we get these projective double cross formulas with S1 and S3 now being the spreads of the quadrilateral. And again, this is the symmetric form of the projective double cross formula. Okay, so that's it. To summarize, go back up to the top here. To summarize, I have presented the projective double cross formula, and it gives a relation between, for a quadrilateral consisting of points A1, A2, A3, A4, side quadrants is Q1, Q2, Q3, Q4, and spreads S2 and S4, then this is the relation that is satisfied, and it's called the projective double cross formula. And down here is the more symmetric form of it. And again, if you set the spreads to 0, then you would end up, these equations would turn into the projective quadruple quad formulas. Okay, thank you for your attention.